Welcome. We have so far learnt the mathematical solutions of the balance equations, and we have seen a few selective ways of solving the mathematical expressions, like we talked about exact, inexact, homogeneous, non-homogeneous, etc. Now, many times we find in our physical systems the balance equations are quite simple, so that you can analytically solve them, and as I told you, any analytical solution will always give us the exact value, okay, because there is no approximations involved as such in those analytical solutions. Okay. And the goodness of the solution will depend on the goodness of the model equations. On the other hand, many times we also find that the expressions for these balance equations are becoming very complex, that it is not feasible for us to adopt any kind of analytical means of solving those equations. In that case, we have to go for numerical solutions. Okay? And these numerical solutions may be for differentiation, may be for integration. Okay. So, in this particular lecture, what we shall see, we will take some numerical solution of the macroscopic balance equations, and in this we shall be focusing more on the differentiation problems, okay, where we shall be having the derivative. In future, we shall be looking into the integration problem. So, first I shall be talking selectively, because in the courses and the books dedicated on the numerical techniques, you will find plenty of methodologies have been proposed and also derived. So, I will not be going into those derivations and all sorts of the methods, but I will suggest you that you please go through the dedicated books or lectures on this numerical analysis, so that you can find out the background of the various methods and their derivation, so that you can go with some different types of numerical techniques and understand their applicability for various types of problems. So, in this lecture I shall be dealing with only a few of the numerical techniques which are used to solve differential equations and which are very commonly used in the domain of this process analysis. So, first let us take up this Euler's explicit method. As I told you in our previous lecture, that explicit and implicit means that if you are able to get the value of the unknown variable in terms of the independent variable, then it is called as explicit, and if you find that the value of the dependent variable has to be found on the basis of not only the independent, but also the dependent variable itself, then it becomes an implicit. So, to make it a mathematical statement, we can say if y is the dependent variable and if y can be found as a function of only the independent variable x, then we call it explicit. Explicit. But if for some reason we find that this y has to be found not only based on x, but also based on the y itself, so it becomes an implicit form. Okay. So, this is the way we distinguish between explicit and implicit. Okay. So, first we shall be looking into the Euler's explicit method, and here we are taking some example that we have to solve this particular expression, that y prime equal to minus 3y, and with we need, whenever we are using any kind of numerical method for solving some differential equation, we go step by step, because what we basically want is this: we want to find out the value of the independent variable at some particular value of the dependent variable away from the initial value. Okay. Now, by integration we can do that very analytically, we can do it very simply, but whenever we are going to the final value, so we find that in when we are going numerically, then we have to take some steps. That means, suppose I have this particular y versus say x, okay, and I am given y prime, okay, this is given, but I have to find out the value of y for different x values. Suppose I am given the value, suppose this is x0, that is, and here I know the value of the y0. Okay, so suppose this is our the initial condition. Okay, so but suppose this is the form of the y. So we have to find the value of y at some other x value. So if I know this particular expression of y, then I can simply take the value of x and I can get the value of y over here. But that is for analytical solution. But when we go with numerical method, what we do is this: we go step by step. That means from this value we find this value, then we go to this value, like this. We go in steps and finally we try to approach this. Now, depending on the numerical technique, we may find that we are not always following the exact function. What we are doing whenever we are going numerically, we are making some assumption for the particular function. So, what happens that even though this may be the true value, what we are essentially doing is this: we may be going from this, we are going towards this, and then moving towards this and moving toward this. Then you will find that at each of the points there is some kind of a deviation in the between the true value and the numerical value. Okay, so you can see that we are getting some kind of deviation at each point of the x. Okay, that means we are approximating the exact solution by some assumed solution, and we are taking that path. Okay, so you find that whenever you are applying any numerical techniques, there will be some error associated with the values of the unknown variables you are solving, because you do not know the exact nature of the particular function. Okay, so numerically we are always approximating the actual variation, and then we are finding the solution. So that what we find essentially is this, that we have so many numerical techniques, and because we are trying to improve upon our approximate value, we want to stay as near as possible to the exact function, but our numerical techniques are not able to do that. And that is why you will find in the literature there are many techniques are proposed to improve the solution numerically. Okay. So, with this understanding, now what we shall do? We shall try to understand that how to find the value of y given that this is the y0 at 1. Okay, and we have to use this Euler's explicit method. I will not go into derivation of this method. I will simply demonstrate it by one example, and I understand that you can understand this method. Okay, so let us go like this. So here this is the formula of this Euler's explicit method. Now here what we have, this is y n plus 1 is equal to y n minus h into, this is the f y n. This is basically this particular representing the given function y prime at n. Okay. So this is the in general the expression for the Euler's explicit method. So in this what we are doing, that this is we are getting from the problem, given problem. Okay, so we are putting this y prime y n over here, and now things become very simple. You can see easily here that this is the unknown, that is this is the value of y at the next time step. Okay, and this value depends on the time step chosen. Okay. Now you can see this particular h value tells us that how closely we are following the actual solution. So it may be so that if the problem is very non-linear, then you can see that this value will matter a lot, and the linearity of the problem, and this particular expression expression is, you can see this is a linear expression. Okay, a linear expression in h. So what it means basically is this, that suppose I have a very linear solution, it is suppose is a y equal to x, then you can see even if I start, suppose this is the y naught at x naught, this is given to us. Okay. Now in this case I can check that, suppose I want the value of the x over here, at this particular x I want the value of y. So here I want the value of y. Okay. Now, because it is linear, I can choose a big h, step size h, okay, and because it is linear, I can quickly go to this particular value. Now, consider another situation when I have a very non-linear variation of y with x. Now, suppose again I make a very non-linear thing, non-linear. Okay. Now, you can see that suppose this is again the value of y naught at x naught, and suppose I want to take the value over here. Now, you can see if I choose the same big h, then what I find that I may be going like this, and in that I will be missing the y values over here. In this region, I will not be able to predict the values properly, because I am going in this particular fashion. Okay. So, in that case what I need to do is this, then I need to take some other value of the h. So, to track this thing I will take a smaller h. So, I will go like this, I will take small steps and I will try to move like this, okay, so that I can stay near the actual variation. Okay. And you can see that the smaller the value of h we take, the closer we can stay along the actual nature of the variation of the particular dependent variable. So, that is how this step size plays a great role in deciding the accuracy of the solution, and whenever you are solving numerically, you should be aware that how to get this particular step size. Now, let us come back to this problem. Now, you can see that by the given step size, what we are doing now, we are now trying to predict the values of the y for the future time instance. So, here we can simply write that we put the value of time and we put the various values of the yn which we are predicting by this particular method. So, we have these are the different values of the y, and now you can check that how good these values are. Incidentally, for this particular problem you can see that in this problem the analytical solution can be found very easily. So, you can see that it is dy by dx equal to minus 3y, okay, and you can see that y is equal to e to the power minus 3x plus c. So, this is the exact value of the particular thing. So, here I will put this in terms of t. So, let me put this in terms of t, this is not x. Okay. So, this will be t, it will be t here, and here also it is not x, it will be t here. Okay. Now, once you have this particular analytical solution, and you can find also the value of the c from this particular given thing, you can see that for y naught, that means at t equal to 0, y equal to given as 1. So, you can put this value in, you can see that c is equal to, then this is 1 minus e to the power minus 0, that is 1 minus 1 equal to 0. That means your solution is e to the power minus 3t. Okay. So, this is the exact solution. Okay. Now, to check that whether you have chosen this particular h value correctly or not, what you can do is this. You can now put another column here and you can start finding the value of e to the power minus 3t and put it, and then you can check that how well or how badly these numerical values are approximating the actual solution. And you can easily also check that by varying this value of the h or the step size, you will see that these prediction values will also keep changing. And you can find out also that how well or what is the optimum value of h which will be able to give us the best result. By optimum I mean that after as you keep changing the x, you will find that after you change the x, you will find there will not be much of change in the predicted values. So, you can take that to be the h, means when you keep decreasing the h value for any kind of nonlinear problems, this is a nonlinear problem. So, you find that the decrease in h value will also keep the numerical solution near the exact solution. But what you will find that as you keep decreasing h, after certain h you will find there is not much change in the value of the predicted values. That means you are reaching a precise value. So, after reaching a precise value, you can also check about the accuracy of the value by comparing it with the true solution. Okay? So, you will find that whenever you are getting the precise value and the precise value is also becoming accurate value, then you should stop changing the h. And if you find, suppose you take two h value step sizes, say h1 and h2, and in that case you will find that h1 is more than h2, but the precision you will find that they are reaching the precision. Okay? So, what you should do, that you should choose the higher value of the step size, because if you choose the higher value of the step size, then the time for computation will get reduced. Okay? So, that is how we choose the step size for the numerical solution. We want to be precise, accurate, at the same time fast. So, all these three things have to be taken into account to decide this numerical method as well as the step size to be chosen. Now, we come to another problem. Here we have integration problem for this y sin y, and here again we have to predict the value of this y at some other value, and here we have to use the implicit Euler technique. Okay, let us see how the technique looks like. So, here you see this is the Euler technique, this is the expression for the implicit Euler technique. So, here you can see that this is basically the y prime value, okay, which is coming from the given expression. Okay, so, now this y prime is put in terms of the future value that is to be predicted. Okay. So, that is how, if I put this y n plus 1 as y n, it becomes explicit. If I make this thing y n plus 1, this becomes implicit. Okay. So, there is a small difference in this implicit and explicit, but actually this is y n plus 1 equal to y n minus h into y prime. Okay. So, this is the actual expression for this implicit method. Now once you put this value, okay, now you find that on both the sides you have y n plus 1, and this gives rise to, you cannot have it in a straightforward manner for the y n plus 1. And here again you see that this is a nonlinear equation you are having, and for nonlinear equation you should adopt some nonlinear technique of solution, as I have described in the earlier lecture. You can use secant method, you can regular fallacy, bisection, Newton-Raphson. So, all these methods may be used to find out the roots of this equation, okay, to solve these equations. So, what we are doing, that we are using this particular method by successfully substituting it. So, we are putting the next value in terms of this particular value. Okay, and as I told you in my earlier lecture, this is not the unique choice for y n plus 1 k plus 1, you can choose any other ways of finding the y. Okay. So, if you choose this particular thing, and you can see that starting with this initial value, and we have to find this by iteratively, for at each step you have to do iteration to converge. Okay. So, whenever you want to trace the transient phase of the particular function variation, you must by this method you have to keep on iterating at even step to get the solution. Now, please understand this, that if we are not interested in tracing the transient, then the number of iterations for convergence will be reduced, because our aim is for a steady state solution. So, you can see that earlier what I have shown you, that from transient solution also I can get the steady state solution. Okay. And this is often done in the process analysis in CFD, that we do not solve a steady state equation, but we solve a transient equation and to get the solution at steady state. So, in this case also, depending on whether you want or do not want to trace the transient of the process, you have to keep converging, or you have to decide the convergence criterion at each particular step. Okay. So, here we are just doing this, and we have shown you the final results for this particular problem. Coming to another technique, that is the Crank-Nicolson. This particular technique we call it semi-implicit or semi-explicit method. What it does is this: in the explicit methods are fast because we don't have to iterate, okay, but they have the problem of stability, that means conversion or getting the right value. Okay. On the other hand, when we go with implicit methods, what we find that they are slower than the explicit method, but they ensure more stability to the solution than the explicit methods. Okay. Now, both of them have their pros and cons. Now, when we adopt any kind of semi-explicit or semi-implicit method, what we are trying to do is this: we are trying to take the advantage of both these types of methods. That means, we want to make them faster as well as we want to make them more stable. Okay. So, in one of these formulations, we have Crank-Nicolson. It is a very popular technique in numerical methods. Okay. So, I am discussing only this particular method, and please understand there are many other such kind of methods in the literature. So, here we have this particular given expression here, and what we are going to do is this: we will not be going for the. So, here what we are basically doing is this particular thing, this right hand side, what it basically represents is this: it is representing that y prime at n, y prime n plus 1, and we are taking the average of this. That means, we are giving weightage to the values at the previous time step or the previous value of the independent variable and the present value of the independent variable. That is how this becomes semi-implicit, explicit or implicit. Okay. Now, with this particular understanding, what we are now doing is this: we are getting this particular expression, and you can see in this we have both sin y n and sin y n plus 1. And you can see that we have to solve because of this implicit nature. Again, we have to do iteration to get convergence at each successive value of the x or time. So, we can again perform this thing, and we find that these are the solutions. Now, if you compare this solution with the earlier solution, you can find that if you count the number of iterations involved to get the convergence and also stability, you will find this Crank-Nicolson is generally working better than the implicit methods, but it is not so fast as the explicit method, but it is at least ensuring the stability which is not there in the explicit method of solution. Okay. So, this is a very popular method of solution of the differential equations. Another method is very popular, that is predictor-corrector. It is somewhat like the combination of the implicit and the explicit methods. So, here we shall again see how this is done. So, here we are taking this same function we are taking, and what we are doing that this particular method needs more than one value to start up. Okay. In earlier methods we needed only one value of y for some value of x, but here we need more than that. So, here we have 1, 2 and 3, and these many values are needed. And understand one thing, there are many types of these predictor-corrector methods in the literature. I am showing only one of them to you, and if you check the literature, you will see there are many other methods, and you can adopt the particular method depending on the problem at hand. That means, you have to decide case by case basis which method is going to work best for your system. Okay. So, here I have shown one, and for that we find that we have plenty of values to start with y0, y1, y2, y3, and to get the value of y4. Okay. Let us see how we do that. So, here we have these two. So, here by P we mean predictor and by C we mean corrector. Now, you can see that these two formulations are a bit different. The first formulation you can see that y n plus 1 is put in terms of all the previous value of y n which are known or which are supposed to be known. Okay. And you can see this that means we are having an explicit way of finding the value of y n plus 1 in terms of the previous values. Okay. Now, here you find this is putting as overbar. And once we know this value, then this value is taken for the corrector method, which is, you can again see, this is an implicit in y n plus 1. So, here is y n plus 1, this corrected value, and this is the y over bar n plus 1, which is obtained from the explicit expression. So, this is a corrected equation, the predicted equation. Okay. Now, the thing is this, once you are given some value of the previous steps, so what you can do, you can find easily this particular value of y over bar. Once you get this value of y over bar, then you can come to the corrector method. Okay, and then you can update the value of y n plus 1. But one thing you must understand, that there is no need to stop at one application of this corrector equation. You can apply the corrector equation many times. Once you do this predictor method, then you can apply the corrector method multiple times to get updates of this y value until you get convergence. That means, if I write in these terms, what I can write this, I can have one predictor, one corrector. I can have one predictor and two corrector, and then I can have one predictor, three corrector. So, you can see that this can go to many numbers, okay, depending on the kind of accuracy you need in your solution. Okay, and this is quite straightforward. You don't have to solve any kind of differential equation or don't have to solve any kind of integration. Simply by an algebraic expression, you are able to get the solution. Okay. And now the another issue comes in this particular solution is this, how to start this one, because initially we may know this y n, but what about these y n minus 1, y n minus 2, y n minus 3. So, for this what is suggested is this, that because these PC methods are supposed to be better than the Euler's method, then what you can do is this, initially you take smaller step size and use the Euler's method, either explicit or implicit, to generate these few values. Okay. So, suppose you want the value of y4. Okay. So, y4 should depend on y3, but to get the value of y3, what you do, you can start with y0, get the values of the y1, y2 and y3 by applying the Euler's method. Okay. And after you obtain that, then you switch over to this predictor corrector method, now so that you can now take a bigger step size, and so that you can go to the convergence faster. Okay. So, that is how we say that the starting problem which is encountered in this kind of methods may be overcome by putting some other method. That means, we are hybridizing the methods. Okay. That is how we apply the predictor corrector method. And here I have shown you the values of the y n. Okay, y that is required in this particular problem. So, here you can see that we have applied this thing and we are showing the results to you. So, I will not go into details of these things, you can solve easily these values. So, first we are predicting and then correcting, and as I told you that there could be multiple number of corrector for better accuracy of the particular problem. And next we come to another very popular method, that Runge-Kutta method, and this method has also its many variations. So, I am talking about one of the Runge-Kutta methods. This is kind of a family of methods, you can say. Okay. So, it has, depending on the order of accuracy needed, we have first order, second order, like this. So, this fourth order Runge-Kutta is very popular. Even in fourth order, you will find there are many variations in the literature. Okay. So, I will just give you the expressions to find out the value of the y for the fourth order Runge-Kutta Gill technique, that Gill improvised upon Runge-Kutta method to get this particular solution technique. Okay. So, here we have these particular expressions for the dy by dt, and this is the initial value of y naught, and we have to, with this h, we have to find the value of the y. Now, here is it is that here this is the particular expression, this is the heart of the expression which has to be used for this Runge-Kutta method. This is the particular expression, And here we will find that all these values of A, K1, B, K2, C, K3, D, K4, all these things are obtained from some expressions given by this Runge-Kutta-Gill. So, these are the particular expressions for A, B, C, D. Similarly, you have these expressions for K1, K2, K3, K4. Generally, these expressions are not to be remembered, they will be given to you. You simply have to refer to these equations and keep evaluating the values of A, B, C, D, K1, K2, K3, K4. Okay? So, there is nothing to cram in this for this particular method. And now, it becomes very simple to you. You can see that here that this K1 depends on the initial values of y and t, then depending on then once you find K1, the K2 is dependent on the step size and the K1 value, then K3 is a function of the step size, the K1 value and K2 value, K4 is a function of again step size, the K2 value and the K3 value. That means, you have to go in this particular order. You cannot take any haphazard way of finding the K1, K2, K3 failure, because there is a particular direction of the dependency of these 4 parameters that you have to take care of. And here we have shown you this, that here you can check the values of K1, then the K2, then the K3 and the K4. These have been obtained from the earlier formulae, and using those and the values of the A1, A, B, C, D, we can find that the value of this particular this y for the next time steps. Okay. So, here are the references in which you can find more details about the methods I taught you today. Thank you.